Hey YouTube, in this tutorial you'll learn how to read temperature from DS18B20 with STM32 F103C8 without delay by using timer and DMA to implement Maxim one-wire protocol. If you find this tutorial hard to understand, go watch some of my other videos on timer first. I put a link in the description. This is wiring. Remember, sensor and MCU can't be able to connect bus to ground. MCU has to be able to do three kinds of operation. Reset is just a one pulse. Second operation is sending a byte. These bytes are commands. And third one is receiving 72 bits. To read temperature, MCU has to do this instruction in this order and a specific timing. I start with sending a command byte. To send a byte, MCU has to send 8 bits. This is how MCU has to send 1 bit. To write a 0 bit, master has to send a write 0 slot on one wire bus. A slot is how bus behavior has to be to do an operation in a specified portion of time. Write slot's duration has to be at least 60 microseconds with 1 microsecond recovery time after sending each slot. Both write 0 and write 1 time slots start with master pulling bus low. To write 1, master releases bus within 15 microseconds. To write 0, master pulls bus down for duration of a slot. This is how I'm going to implement it. For both writing 1 and 0, time slot starts by master pulling bus low. To write 1, master releases bus after 10 microseconds. To write 0, master pulls bus down for duration of time slot. Write slot's durations are 70 microseconds and there is 10 microsecond recovery time after sending each slot. This was requirement for writing a bit. Next step is reading 1 bit. To read 1 bit, MCU has to pull bus low for at least 1 microsecond and release it within 15 microseconds. I did 10. After MCU releases the bus, DS18B20 controls bus behavior by pulling bus low or let it remain high. There are read 0 and read 1 time slots with minimum of 60 microsecond and 1 microsecond recovery time after sending each slot. Both slots starts by master pulling bus low. Then sensor transmits 1 by leaving bus high and transmits 0 by pulling bus low. This is how I'm going to implement it. In both read time slots, MCU is going to pull bus low for 10 microseconds. Then MCU releases the bus and bus is going to be pulled up. If sensor is transmitting 0 bit, sensor is going to pull bus low. If sensor is transmitting 1, sensor is going to let bus be high. My task is to make this kind of pulses. But if you're using an MCU which does not have good enough peripherals to do this operation, you have to write a code. This is the code that I have to write to generate write 1 slot. First step, MCU has to pull bus low. This is done by HAL GPIO write pin to change GPIO pin state. Second step is a 10 microsecond delay. In third step, MCU releases the bus. This is done by changing pin configuration to input. Then there is a 7 microsecond delay. It's called software implementation because every time you want to do this operation, this code has to be executed. And it takes a lot of CPU time because CPU is responsible for executing code. There are tutorials on YouTube on interfacing DS18B20 with STM32 that uses this approach. It's easier to learn and good opportunity to check sensor and wiring. I put a link in the description. Alternative approach is to use peripherals, in this case timer and DMA, to do as much as they can, so CPU has less things to do. In this approach, CPU job is reduced to just initializing timer and DMA one time and starting these operations. And timer and DMA take care of rest of the job. And it's much less CPU load compared to software implementation when you use CPU for everything. This is my starting point. I have a project named DS18. This is a copy of LCD DMA project. LCDDMA.c and DMA.h are in lib folder. Because I want to show things in LCD, new file, add a header file named DS18.h to lib folder. Again, right click on lib, new file, add a source file named DS18.c. In DS18.h, write hash pragma once, then include general.h. This header file is just CMSIS header file, IT header file, and system header file. Now go to DS18.c hash include DS18.h. Also include DS18.h in main.c. Compile again. Go to DS18.c. Add a function here with the return type of void named DS18 init. Input is void. I start by doing GPIO configuration. To read bus, I want to use pin PB6, which is timer for channel 1 input, and to connect one wire bus to ground with this transistor, I want to use pin PB8, which is timer for channel 3 output. First, I have to enable GPIO peripheral clock by setting bit IOPBEN. RCC arrow operator APB to ENR bitwise or assignment with bit mask to set a bit. I want to set bit IOPBEN. Pin PB8 has to be in alternate function push-pull configuration. Mode 8 has to be 10 output mode, and CNF8 10 alternate function output push-pull mode. In first line, I clear both mode 8 and CNF8 bits by doing bitwise and assignment with not of bit mask. In the second line, I set mode 8 bit 1 and CNF8 bit 1 in CRH register by doing bitwise or assignment with bit mask. PB6 is input float, and mode 6 has to be 00 input mode, and CNF6 has to be 01 floating input in GPIO BCRL register. First, I clear 4 bits of mode 6 and CNF6, and in this line I set CNF6 bit 0. Start timer for configuration by setting TIM4EN bit in APB1 ENR register to enable its clock. RCC arrow operator APB1 ENR bitwise or assignment to set a bit. I wanted to set bit TIM4EN. For counter to be in upcounting mode, CMS and direction bits should be cleared in CR1 register. Timer for arrow operator CR1 register bitwise and assignment with not of bit mask to clear bits. I wanted to clear CMS and direction bits. Next step is setting ARPE bit in CR1 register, so ARR register is buffered. This is enabling preload capability for ARR register, and because I have to change ARR, I have to set this bit. With this bit set, ARR value changes just at update events. Timer for arrow operator CR1 register to set a bit bitwise or assignment with bit mask. I wanted to set bit ARPE to enable preload for ARR register. Next step is calculating ARR and PSC for timer 4. These are read and write time slots. With 10 microsecond recovery time, they all are 80 microseconds. So timer for counter period is 80 microseconds. CNT clock period is 1 microsecond. It is CNT and CCR registers unit of time measurement. So ARR is 79 and PSC is 71. ARR is 79 and PSC is 71. But reset pulse is different than read and write time slots. It starts by master pulling bus low for at least 480 microseconds. Then master releases the bus, and then DS18B20 has 480 microseconds to send its presence pulse and pull bus low for 60 to 240 microseconds. This is one wire bus behavior during reset pulse. Black is when bus is pulled up by resistor. Green is when bus is pulled down by DS18B20, and red is when bus is pulled down by MCU. In my implementation, master pulls bus low for half a millisecond, and there is a half a millisecond time for sensor to send its presence pulse. To send reset pulse, I want counter period to be 1 millisecond, and I don't want to change CNT clock period. So ARR for reset pulse is 999, and PSC is 71, same as before. Next step is configuring timer for channels. Timer for channel 1 input is connected directly to one wire bus. It is going to capture rising edges, and it's used for reading 72 bits. Timer for channel 3 is used to connect one wire bus to ground with a transistor. Start timer for channel 3 configuration by setting OC3PE bit in CCMR2 register to enable preload for channel 3. Timer for CCMR2 bitwise or assignment to set bit. I want to set OC3PE to enable preload for channel 3. Next step is clearing CC3S bits in CCMR2 register, so channel 3 is configured as output. Timer 4 arrow operator CCMR2 bitwise and assignment with not of bit mask to clear bits. I want to clear CC3S bits. But when you're enabling preload, channel can't be in output mode. Here I write timer 4 arrow operator CCMR2. In this line I set CC3S bits, so channel 3 is not in output mode. Then I enable preload, then channel 3 is in output mode. All of time slots and reset pulse start with master pulling bus low and then releasing bus. And that's all timer 4 channel 3 is responsible for. Pulling bus low at the start of this time slots and reset pulse. So with what kind of configuration for channel 3 I can generate this kind of pulses? It looks like PWM mode 2. Channel 3 has to be in PWM mode 2 configuration and it has to be active low. PWM mode 2 is OC3 ref pulse. It goes through output control and then it is timer for channel 3 output. Pay attention, when timer for channel 3 output is high, bus is low. When timer for channel 3 output is low, bus is high. Because this NPN transistor is inverting this pulse. So if bus behavior looks like PWM mode 2 and I want OC3 ref to be PWM mode 2 and NPN transistor inverts channel 3 output, if I invert it another time, these two cancel each other. This is why channel 3 has to be active low. For channel 3 to be in PWM mode 2, OC3M bits in CCMR2 register has to be 111. Timer 4 arrow operator CCMR2 register to set bitwise or assignment with bit mask. For channel 3 to be in PWM mode 2, I want to set OC3M bits. PWM mode 2 is OC3 ref and it has to be inverted. This is done by setting CC3P bit in CCER register. Timer 4 arrow operator CCER bitwise or assignment to set a bit. I want to set bit CC3P. Channel 3 is responsible for all of time slots and reset pulse. For reset pulse, ARR has to be 999 and CCR3 is 500. So there is a half millisecond low time in a 1 millisecond pulse. In write and read time slots, ARR is 79. In write 1 time slot, CCR3 is 10. So MCU pulls bus low for just 10 microseconds and then releases the bus. In write 0 time slot, CCR3 is 70 microseconds. So MCU pulls bus low for 70 microseconds. In read 1 and read 0 time slot, CCR3 is 10. Because in both this time slot, MCU has to pull bus low for 10 microseconds. So to send different bits or to read bits, I just have to write value to CCR3. But what happens before and after performing a time slot or a reset pulse? Before and after time slots, bus is in idle state. It's pulled high. And OC3 ref is like one wire bus because it's inverted twice. And in PWM mode 2, if CCR is 0, counter is always bigger or equal to CCR. So output is high. So by putting CCR3 to 0 before and after time slots, we make sure channel 3 output is not trying to pull bus down. Next step is timer for channel 1. I use channel 1 just for reading 72 bits. Every time a rising edge happens on one wire bus, CNT register is stored in CCR1. In read 0 time slot, rising edge happens only one time. But in read 1 time slot, rising edge happens 2 times. It means 2 CNT values stored in CCR1 and the first one is overwritten. If at the end of this period, like at update event here, I read CCR1 register, based on value of CCR1 I can decide if I read 0 or read 1. Pay attention, CCR3 value is 10 and channel 3 is doing its job for pulling bus low and then releasing it after 10 microseconds. To configure channel 3 in input mode and connecting TI1 to IC1, CC1S bit in CCMR1 register has to be 01. First I clear both CC1S bits and in this line I set bit 0 of CC1S. So CC1S is 01. Channel 1 has to capture on rising edges of IC1. CC1P is 0 in CCER register. Clear CC1P bit in CCER register by doing bitwise and assignment with not of bit mask. Enable channel 1 by setting CC1E bit and channel 3 by setting CC3E bit in CCER register. Timer 4 arrow operator CCER bitwise or assignment with bit mask. I want to set bit CC1E and CC3E to enable channel 1 and 3. Next step is writing a function that initiates generation of reset pulse. Reset pulse is also a PWM mode 2 pulse. This is OC3 ref, 1 millisecond period with half a millisecond low time. And this is one wire bus. After MCU releases the bus, sensor can send its presence pulse. Before DS18 init add a function with return type of void and input argument of void. In first line, timer 4 is disabled by clearing CEN bit in CR1 register. To send reset pulse, ARR has to be 999 and CCR3 has to be 500. After you write these values to ARR and CCR3, you have to generate an update event. ARR and CCR3 are preloaded. It means values are not saved in these registers until an update event happens. And that's what I did in this line. I generated an update event by writing 1 to UG bit in EGR register. In the next line, timer 4 counter is enabled. After this line, when CEN bit in timer 4 CR1 register is set, reset pulse starts and timer 4 starts counting. With 999 for ARR and 500 for CCR3. These are required values to have a pulse with 1 millisecond period and half a millisecond low time. After reset pulse finished, for the next timer 4 cycle, I want ARR to be 79 and CCR3 to be 0. That's what I wrote. After enabling timer 4, I wrote 79 to ARR and 0 to CCR3. Remember, ARR and CCR3 are preloaded. It means it doesn't matter when you write in these registers. Value is going to save in these registers when an update event happens. So after timer starts counting, in this line I changed ARR and CCR3. But these values are not going to be saved in ARR and CCR3 until an update event happens here. That's how you change ARR and CCR3 for the next cycle with preload capability. In next step, I try to explain to you how timer for channel 3 and DMA1 channel 5 are going to work together to send a command, which is 8 bits. To send each bit, CCR3 value has to change according to bit value. If you want to write 1, CCR3 has to be 10. If you write 0, CCR3 has to be 70. In this example, I want to send 0f command. For 0f command, I define an array with 9 members of type uint16t, like CCR3 register. This array stores 9 values that are going to be written in CCR3 register by DMA1 channel 5. CMD0 stores CCR3 for bit 0. Value for bit 0 is 1, so CCR3 has to be 10. CMD7 stores CCR3 for bit 7. Bit 7 value is 0. CCR3 has to be 70. CMD8 is 0 because after sending command is finished, CCR3 has to be 0 for one wire bus to be in idle state. In all these 3 examples, counter is counting from 0 to 79 and counter period is 80 microseconds. In 3 cases, you see when timer for channel 3 DMA request and when timer for update event happens. Timer for update event happens at end of the period and timer for channel 3 DMA request is sent when CNT and CCR3 value are equal. When CCR3 is 0, channel 3 DMA request happens at a start of period. When CCR3 is 10, channel 3 DMA request happens when CNT is 10. And when CCR3 is 70, channel 3 DMA request happens when CNT is 70. Sending a command is started by CPU executing DS18 send CMD function. After this function is finished, CCR3 is a seed 0 and bus is in idle state. In the next timer for channel 3 DMA request, which is at the same time with update event because CCR3 is 0. A request is sent to DMA1 channel 5 to transfer CMD0 to CCR3. And after DMA1 channel 5 transfers CMD0 to CCR3, CCR3 is not going to change right away. It's still going to be 0 until next update event happens, which is here. Now for the next cycle, which is bit 0, CMD0 is stored in CCR3. During sending bit 0, when timer for channel 3 DMA request happen, a request is sent to DMA1 channel 5 to transfer CMD1 to CCR3. CMD1 stores value for bit 1 and after DMA transfer happens, value is not going to be stored in CCR3 until next update event happens, which is here. When bit 7 is being sent and timer for channel 3 DMA request happens, DMA1 channel 5 transfers CMD8 to CCR3 and CMD8 value is 0. So after the next update event, CCR3 value is going to be 0. CCR3 has to be 0 for one wire bus to be in idle state. I add 3 definitions for 3 values to be written in CCR3 register. 10 is defined 1 to write bit 1, 70 is defined 0 to write bit 0, and 0 is defined idle when you want to put one wire bus in idle state. I want to use 3 commands, so I write 3 arrays each with 9 members of type uint16t. First member is CCR3 value for bit 0. Second member is CCR3 value for bit 1. And last member is CCR3 value for one wire bus to be in idle state. Skip run value is CC in hex. It's 11001100. If you start from least significant bit, it's 00110011. 00110011. You have to start with least significant bit. This function has to be executed before sending each command. To start timer for channel 3 and DMA1 channel 5, so they do the operation. The only CPU load for sending a command is this function, which starts and finishes before operation starts by timer and DMA. Compare it to software implementation where CPU is busy from start to finish. First step in this function is disabling timer for counter by clearing CEN bit in CR1 register, because I don't want timer for update event to happen during execution of this function. Then you disable DMA1 channel 5 by clearing EN bit in CCR register, because I have to change DMA1 channel 5 CMAR and CNDTR register, and when you want to change these register, channel has to be disabled. CMAR is memory address. It's the array that holds 9 CCR3 values for a command. CNDTR is number of transfer, and it's 9. Then DMA1 channel 5 is enabled by setting EN bit in CCR register. And last step in this function is enabling timer 4 by setting CEN bit in CER register. Next step is writing a function to start receiving 72 bits. Here you see the 0 and 1 time slots. They both start by timer for channel 3 pulling bus low and releasing it after 10 microseconds. If sensor pulls bus low, it's sending 0. If bus remains high, sensor is sending 1. Timer for channel 1 is in input capture mode and it's directly connected to one wire bus. Whenever a rising edge happens on one wire bus, CNT value is saved in CCR1. In read 1 time slot, rising edge is here, and CNT register is saved in CCR1 when CNT is 10 or 11. In read 0 time slot, rising edge happens 2 times. First when CNT is 10 and second time when CNT is 70. If I read timer for CCR1 register after read time slots are finished, I would see the last value that is stored in CCR1. If it's 70, it's read 0 time slot. If it's 10, it's read 1 time slot. To receive 72 bits, I have to know 72 CCR1 values. At the end of each of 72 read time slots, timer for update sends a request to DMA1 channel 7 to transfer timer for CCR1 register value to an array in memory. This array has 72 members for 72 CCR1 values. DS18 receive is the function that starts timer 4 and DMA1 channel 7 to receive 72 bits. Like send CMD function, first you have to disable DMA channel and timer 4. Now DMA channel is DMA1 channel 7, and at the end of the function you have to enable DMA1 channel 7 and timer 4. CNDTR value is number of transfer and it's 72. Read time slot is the definition for 10. You have to write 10 in CCR3. So channel 3 pulls bus low for 10 microseconds at the start of each read time slot. Because CCR3 is preloaded, this value is not going to be saved in CCR3 until an update event happens. And that's what I did in this line. By writing 1 to UG bit in EGR register, you can generate an update event. In next step, you have to disable update DMA request for timer 4 by clearing UDE bit in DIER register. And in the next line, you have to enable it by setting UDE bit in DIER register. I don't have an explanation that is based on reference manual for doing these 2 lines. But if you delete these 2 lines, this code is not going to work. It's like there is an update DMA request flag. And by disabling DMA request and re-enabling it again, you clear that flag. At the end, you have to enable DMA1 channel 7 and timer 4. Write DS18 send command function before DS18 init. Next, I'm gonna define a global variable of type uint16t asterisk and name it DS18CMD. Before calling this function, I'm going to store array address for each command that I want to send in DS18CMD variable. After DS18 send CMD, write DS18 receive function. For CCR3 value, instead of using this definition, I just write its value. To generate read time slots, CCR3 has to be 10. Compile the code. There is 2 errors. Click on problem, errors. I forgot to write definition for bus 1. Bus 1 value has to be 0. CCR value has to be 0, so one wire bus is in idle state. Compile again. There is no error and warning. I continue by doing DMA configuration. First, you have to enable DMA1 clock by setting DMA1 EN bit in AHB ENR register. In DS18 init function, after timer 4 configuration, start doing DMA configuration by setting DMA1 EN bit in AHB ENR register in RCC peripheral. This is DMA1 request mapping. It shows what DMA1 channel your desired peripheral request signal is connected to. I want to transfer a half word from CCR1 register in timer 4 to CCR array in memory after each timer 4 update event. This event is connected to DMA1 channel 7. That's how I know I have to use channel 7. For timer 4 update DMA request. To send the command, I need a DMA channel that transfer 9 half words from an array in memory to timer 4 CCR register with 9 requests from timer 4 channel 3. Timer 4 channel 3 DMA request is connected to DMA1 channel 5. Start DMA1 channel 7 configuration by enabling its request from timer 4 update event by setting UDE bit in DIER register. CMAD register is memory address. It's the base address of the memory area which is going to be read from or written to. And with each of 72 requests from timer 4 update event, DMA1 channel 7 transfer a half word from timer 4 CCR1 register to CCR1 array in memory. DMA1 channel 7 CMAD register assignment. CCR1 is name of an array with 72 members of type uint16t. Its type is uint16 asterisk, and you have to cast it to write it into a uint32t. At the start of this file, I defined CCR1 array with 73 members. CPAR is peripheral address. It's the base address of the peripheral data register that DMA channel is going to read from or write to. DMA1 channel 7 is going to read 72 half words from timer 4 CCR1 register. You have to write timer 4 CCR1 register address to CPAR. DMA1 channel 7 arrow operator CPAR assignment address of timer 4 CCR1, and don't forget to cast it. And in CNDTR register you have to write number of transfers, but you have to do it each time you want to use DMA channel. But I write it here too. Start DMA1 channel 5 configuration by enabling its request from timer 4 channel 3 by setting CC3DE bit in DIER register. CMAR is memory address. Every time you want to send a command, you have to change CMAR register in DMA1 channel 5, and I'm not going to change it here because every time I want to send a different command. CPAR is peripheral address, and for DMA1 channel 5 it's address of timer 4 CCR3 register. DMA1 channel 5 CPAR assignment, don't forget to cast it, address of timer 4 CCR3. And number of transfer for channel 5 is 9. It's not necessary to write this line here because every time I want to use DMA channel, I have to write number of transfer in CNDTR value. Next step is configuring CCR registers for channel 5 and channel 7 in DMA1. This is DMA channel configuration register. Values for bits that I specified here is the same for channel 5 and channel 7. Mem to mem bit is cleared, memory to memory is disabled. Priority is not important, and for both channels is 00 low. M size is the size of data that is being read from or being write to memory, and for both channels it's 16 bits. M size is 01. P size is also 01. Minc bit is set because memory increment mode is enabled. Pink is cleared, peripheral increment mode is disabled for both channels. Circular mode is disabled for both channels. And transfer error and half transfer interrupts are disabled for both channels. These bits are 0 also. I start doing CCR register configuration for channel 5 by writing 0 to CCR register. I do it also for channel 7, writing 0 to CCR. These are bits that have the same value for channel 5 and 7. I write the same exact line for channel 5. It is setting P size bit 0 and M size bit 0 and minc bit. For DMA1 channel 7, data is being read from peripheral registers and direction bit is 0. For DMA1 channel 5, data is being read from an array in memory and direction bit is 1. So I add bit mask for direction bit in this line that I'm setting bit in CCR register for channel 5. For DMA1 channel 7, I want to enable transfer complete interrupt. So at the end of receiving 72 bits, I can calculate temperature. Add bit mask for setting TCIE bit in the line that I'm setting bits in CCR register of DMA1 channel 7. After this line, transfer complete interrupt is enabled in DMA1 channel 7. But before you enable any interrupt, you have to clear its flag. And this is what I did in this line. Clearing transfer complete interrupt flag for channel 7. Next, define a variable of type uint32t, name it PG priority grouping, call nvic get priority grouping, and write output of this function to PG variable. Priority grouping is going to be stored in PG variable. Next, call nvic set priority. First input of this function is interrupt number. DMA1 channel 7 has one interrupt and its interrupt number is DMA1 channel 7 IRQN. Second input is the priority that you want for this interrupt. To give priority, you use nvic encode priority. First input is going to be PG variable. Second input is preemption priority. I put 4, and for sub priority I write 0 because there is no bits for sub priority. Next step is enabling interrupt by using nvic enable IRQ function. This function has one input and that's interrupt number. To write the callback function, at the start of this file I write a function with return type of void. Input argument is void. To specify this function as callback function for DMA1 channel 7 transfer complete interrupt, you have to write this function address to a specific function pointer variable. This function address is name of this function. Before enabling interrupt, this function address has to be written in a function pointer variable. To access this function pointer variable, write x callback DMA1 channel 7. This is the name of an structure. You put dot after it, you can access its members. 3 members of this structure are function pointer variables. I have to store my function address in TC function pointer variables to specify callback function for DMA1 channel 7 transfer complete interrupt. Compile the code. Received 72 bits consist of DS18B20 scratchpad memory, which is 8 bytes, and CRC byte. I store a scratchpad in a variable of type uint64t, and I store CRC in a variable of type uint8t. Next step is calculating 72-bit values that are in DS18-bit and DS18 CRC variables. Reminder 1. For each bit, there is a CCR1 value. If this value is less than 15, that bit is 1. Reminder 2.1. Bit mask and bit number. For example, for bit 4, bit mask is a value with all bits 0 except bit 4. And this is how you can make it. 1 left shift bit number. And for this bit, bit number is 4. And bit mask is 1 left shift 4. Imagine at first 1 is here. Left shift 1, left shift 2, left shift 3, left shift 4. And this is bit mask for bit 4. Reminder 2.2 setting a bit. In this example, I want to set bit 4 in a variable. I have to do a bitwise OR with bit mask for bit 4. Then I have to store result of this operation to a variable itself. This line can also be written like this. A bitwise OR assignment with bit mask. I wanna replicate DS18B20 scratchpad memory in DS18 bit variable. Temperature least significant bit has to be the byte with the lowest address in DS18 bit variable. This is least significant byte of a 64 bit because of little Indian. Bytes order in scratchpad memory is also the order in which these bytes are sent. So temperature LSB is sent first. And first 8 timer for CCR1 register values that MCU receives are in CCR1 array with index 0 to index 7. Now I know which CCR1 array member belongs to which bit. CCR1 0 is representing bit value for bit 0 and CCR1 63 representing bit value for bit 63. It means bit number and array index are the same. This is how you're going to write it. CCR164 represent value for bit 0 in DS18 CRC. This is how you're going to write it. Now a scratchpad is replicated in a 64-bit variable. I also want to access this memory space as 8 bytes to calculate CRC. I also need to extract temperature, which is first 16 bits, and a byte of high threshold and a byte of low threshold, and config byte from this 64-bit variable. To achieve this, I need to access this memory space as an structure with these members that are designed according to a scratchpad memory. So I need to access one address as 3 different types. This is union application. Union is a type of variable that all its members have the same address. And a structure named str, a 64-bit variable named bit, and an array of bytes, they all have the same address. I did a very similar thing with union in DS18B20 tutorial. If you need more explanation, go watch that. DMA1 channel 7 transfer complete interrupt happens after channel 7 stores 72 timer for CCR1 register value in CCR1 array. 3 things has to be calculated in this function: values for 72 bits, CRC, and temperature. Start this function by writing 0 to CCR3 register. Because after 72 bits are received, I want bots to be in idle state, so CCR3 has to be 0. In the next step, disable DMA1 channel 7 by clearing EN bit in CCR register. It's time to add union definition. Go to DS18.h. I add a type def union. Its name is DS18 scratchpad type, and it's a union with 3 members. For str struct, I used attribute packed to be sure there is no empty spaces here. Compile the code, go to DS18.c. I define a variable of type DS18 scratchpad type named DS18 data. I also need a byte to store CRC. Then there are 2 for to put calculated bits into DS18 data.bit, which is a 64-bit variable, and DS18 CRC, which is a byte. Next step in this function is calculating CRC. Go in lib folder, right click, new file, name it crc.c. Another file, name crc.h. This is what you add in crc.h, and this is what you add in crc.c. Add crc.h inclusion in ds18.h. Compile the code. There is an error in ds18.c. CCR1 array is uppercase. Compile again. This function is going to calculate CRC for first 8 bytes, and it takes its input as an array of 8 bytes. First input is base address of array, and second input is number of bytes, which is 8. This function output is calculated checksum, and if it's not equal to received checksum, which is stored in DS18 CRC variable, received data is considered damaged. If DS18 CRC is equal to output of CRC compute 8 function and DS18 CRC is not 0, received data is okay, else received data is damaged. Because I want to show temperature in character LCD, I have to store it in a float variable. I define a float variable named temp. Temp assignment. I wanted to access a scratchpad as a 64-bit, as an array of 8 bytes, and as an structure. Now it's time to access DS18 data as an structure. I choose str member. This is a structure. You put dot after a structure, you can access its members. I want to access temperature. This is least significant and most significant byte of temperature. If it's right shifted 4 times, 1, 2, 3, 4. Due to power of 0 is going to be here. So I have to divide this by 16 to calculate temperature. If data is damaged, I want temperature to be 1000. Temperature is calculated, and this is the end of operation. And now I have to empty these 2 containers, the 64-bit and 8-bit. I need a buffer to show strings in character LCD. Define a string with size 16. Name it LCD buff. Make a new string and put it in LCD buff with sprintf. Add stdio.h and string.h at the beginning of this file. Compile again. It says the float formatting support is not enabled. Click on Project Properties, C++ Build, Setting, MCU Setting. Use float with printf from newlib nano. Apply and close. Compile again. I also want to use LCD functions, so I add lcd_dma.h. After sprintf, first use lcd set cursor and then lcd print function to print LCD buff in row 1 and column 1. Each DS18B20 transaction sequence has 3 steps. Step 1 is reset pulse. Step 2 and 3 are sending 8-bit commands. But there are 2 types of commands. In step 2 you have to send a ROM command, and in step 3 you have to send a function command. After ROM or function commands there can be data exchange. ROM commands operate on the unique 64-bit ROM code, but I don't want to touch this in this tutorial. The only ROM command that I'm going to use is skip ROM, and these are function commands. To read temperature in the first transaction sequence, I'm going to use convert T, and the second one I'm going to use read scratchpad. To read temperature, you need two transaction sequence. In both of them, first step is initialization, which is reset pulse. Second step is also the same for both transactions. It has to be a ROM command, and for both transactions it's a skip ROM command. In first transaction, step 3 that has to be a function command is convert T command. In second transaction, step 3 that has to be a function command is read scratchpad command. After this command, 72 bits are received, and it's a part of step 3 in second transaction. To start a reset pulse, CPU has to execute DS18 reset pulse function. All of green operation are sending 8-bit commands. To start each of these operations, first CPU has to write command address in DS18 CMD variable. Then CPU has to execute DS18 send command function. To start receiving 72 bits, CPU has to execute DS18 receive function. After CPU starts each of these operations, there has to be a wait state before CPU starts next operation. Each operation has a communication time, and for convert T there is also an execution time. I added something to these values, and for every operation now I have a wait time. Receiving 72 bits takes under 6 milliseconds, but I wanted 1 second wait time after this operation because I thought there should be some time between two consecutive sampling. Wait time for reset pulse is 1.5 milliseconds. It means in this point in time CPU starts reset pulse, and 1.5 millisecond later CPU is going to start a skip ROM operation. 1 millisecond later CPU starts convert T operation, and 0.8 seconds later reset pulse operation. Now the problem is, how can CPU do a set of operations with different wait times? Stop the video and think about it, and you can't use delay. I'm going to start all of these operations in timer3 update interrupt callback function, and to implement different wait times, timer3 counter period is going to be variable, and this is possible because of preload capability. I want CNT clock period in timer3 to be 100 microsecond. So PSC is 7199, and counter period is 1 plus ARR times 100 microsecond. With this formula I can calculate what ARR value is for each wait time. If I want counter period to be 1.5 millisecond, ARR has to be 14. And if I want counter period to be 1 millisecond, ARR has to be 9. In this update interrupt callback function, I'm going to start reset pulse. Wait time after reset pulse is 1.5 millisecond. And in this period, ARR is 14. Next update event is here, and it happens 1.5 millisecond after this one. In this update interrupt callback function, CPU starts operation of sending a skip ROM command, and wait time after this operation has to be 1 millisecond, and ARR has to be 9. Because ARR is preloaded, its value only change at update events. So if I want ARR to be 9 in this period, I have to write value to ARR before this update event happens. Best place is this update interrupt callback function. So in each update interrupt callback function, I also have to change ARR register for the next cycle. That's how you have variable counter period in an STM32 timer. I put 7 steps of this operation in a loop. First is a reset pulse, and wait state for a reset pulse is 1.5 millisecond. For counter period to be 1.5 millisecond, ARR has to be 14. And this value is written to ARR register in timer 3 previous update interrupt callback function. In this update interrupt callback function, also receive 72 bits operation is started by CPU. And for this operation, wait state has to be 1 second. So in this period, ARR has to be 10,000, and this value is written to ARR register in previous timer 3 update interrupt callback function when read scratchpad operation is started by CPU. At the end of this function, start the whole process by enabling timer 3 counter by setting CEN bit in CR1 register. Compile the code and go to DS18.h. I add the type def enumerator named DS18 getTMP type with 7 values for 7 steps of reading temperature. First there is a reset pulse. CCH1 is first skip ROM command. 44 is convert T. RST2 is the second reset pulse, CCH2 is the second skip ROM command, BE is read temperature command, and getTMP read is reading 72 bits. Compile the code and go to DS18.c. I define a variable of type DS18 getTMP type named DS18 status. This value is going to keep track of temperature reading step
that MCU is in. In getTMP function, I write a switch case with DS18 status input. Every time this function is called, DS18 status is compared to these cases. There are 7 cases for 7 steps of temperature reading. In each case, I'm going to write next case in DS18 status, so next time DS18 getTMP function is called, next case is going to be executed. First case is first reset pulse. If this case is executed, next time this function is called, I want getTMP CCH1 to be executed. So I change DS18 status variable. DS18 status assignment getTMP CCH1. It is the next case. When this case is getting executed, next time this function is called, you want getTMP 44H to be executed. So I write 44H in DS18 status. For 44H, next case is RST2. For RST2, next case is CCH2. For CCH2, next case is BE. Next case for BE is read. getTMP read is reading 72 bits. It is the last of 7 steps of temperature reading. Next case is going to be getTMP RST1 to start the process again. DS18 status assignment getTMP RST1. DS18 getTMP function is called every time timer 3 update interrupt happens. And because I want to have variable periods, every time this function is called, I have to change ARR for the next cycle. In RST1 case, I have to change ARR for CCH1. To have a 1 millisecond wait time after first skip ROM command, ARR has to be 9. To have a 0.8 wait time after sending convert T command, ARR has to be 8000. To have a 1.5 millisecond wait time after sending second reset pulse, ARR has to be 14. And ARR has to be 9 to have a 1 millisecond wait time after sending second skip ROM command. Again, it has to be 9 to have 1 millisecond wait time after sending BE command to have a 1 second wait time after reading 72 bits. ARR has to be 10,000. In getTMP read case, you also have to change ARR for the next cycle, which is first reset pulse. And wait time after a reset pulse should be 1.5 millisecond, and therefore ARR has to be 14. Now it's time to start operations. There were 3 kinds of operations. First, reset pulse. To start reset pulse operation, CPU has to execute this command. There is also a second reset pulse. To start receiving 72 bits, CPU has to execute DS18 receive function. In remaining cases, CPU has to start sending a command. In DS18.c, I defined 3 arrays for 3 commands. To send any command, first you have to write that command's array base address in DS18CMD. Then you have to call DS18 send CMD. In getTMP CCH1 case, it's when first skip ROM command has to be started. I write skip ROM CCH array name in DS18 CMD. Remember, name of an array is base address of that array. There is also second time that skip ROM has to be sent. In getTMP 44 case, I write convert T44H array address in DS18 CMD. And for BE case, I write read scratchpad BEH array address in DS18 CMD. Compile the code. Before timer 3 is started for the first time, ARR has to be set for first step of temperature reading, which is RST1. I also have to write getTMP RST1 in DS18 status. Compile, go to main.c, delete LCD set cursor and LCD print, and call DS18 init after LCD init. Compile again. There is a warning, go to DS18.h, add declaration of DS18 init. Compile again. Go to DMA channel 7 transfer complete callback function. In sprintf function, delete this 0. In DS18.c, add 2 variable of type uint32t named ds damaged and ds total. In transfer complete callback function, whenever checksum is not correct, increment ds18 damage by 1. And every time this function is called, increment ds total by 1. So I know how many temperature is sampled and how many damage data there is. Compile the code and go to debug. Run the code. This is the project. Temperature is now 25. This is cold water and this is DS18B20. Temperature is now 18.5, 14.5, 11, 9.5. If I take it out and like put it in my hand, it rises quickly. Now it's 23, 24, 25. Again, I want to cool it. 27, it's now 27, 24, 19, 15, 12, 10, 8, 7, 6. Now I want to warm it again. It's 10, 13. Now temperature is 22.5 and total DS18 total is 60 sampling, 61 sampling is done. There is no damage data. Now around 100 sampling is done. There is no damage data and temperature is 2.5.